All right, so yesterday we left off and we were talking about the different kinds of waves, and we had just watched the big wave surfing video and all of that kind of stuff. So today, I'm going to take out the slinkies. These are lab grade slinkies because they're longer, much longer. Okay, and we're going to demonstrate some of those different types of waves, the transverse, the longitudinal, okay, and then we'll move into talking about the universal wave equation, okay, which is like the second easiest equation you will use in this course, okay, that gets V equals D over T for waves, okay. It's actually V equals F times lambda, so it's even easier than V equals D over T. Right, so it'll be really easy to use, okay, and we'll start looking at that today, and we'll probably do some work on that tomorrow, and then after Christmas we'll pick up with wave behavior, okay, interference, all that kind of stuff after Christmas. We're looking pretty good right now in terms of time. Okay, we should be able to have probably 2 days, okay, for final exam review, maybe 3. Okay, we'll kind of see how it goes. But I'm hoping to have our last unit exam probably that Monday of the last week, or maybe even the Thursday if there's a diploma exam going on that day. Okay, so we'll be looking at that in terms of timing, okay, for us when we come back. Alrighty? Okay, I am going to need a helper for this. Can someone come up and hold, Tyler, come up and hold the other end of this slinky. Everybody else is going to have to come up here because it's going to be on the floor. So if you're going to see it, you're going to have to come up here so that you can see it. All right, I'll have you back up almost to that milk crate there. And then we'll just put it on the floor. Okay, so when we were talking about yesterday, transverse waves. Okay, yeah, come on up, guys. Okay, so remember, a transverse wave is one in which the medium oscillates perpendicular to the direction the waves are going to travel. If I make waves on this slinky, they're going to travel towards Tyler. Okay, but the slinky is actually going to move up and down. Okay, so if I make just one simple transverse wave, okay, the slinky oscillates up and down, but the wave travels in the other direction, perpendicular. Everybody with me on that? Okay, now, when it reflects, if I just make that pulse, when it reflects off Tyler, I made it out to this side. What side does it come back on? The opposite. The opposite side. Okay, when we get to wave behavior, we'll talk about why when a transverse wave reflects, it reflects back inverted. Okay, so those are transverse waves. Now, longitudinal waves are a series of compressions and rarefactions. Okay, so if I compress the spring, that kind of wave looks a lot different. Okay, but you can see where the spring gets more dense and less dense. Okay, so if I push it, that's a compression. You can see the compression. As soon as I move it back, okay, you can see that behind it is what we call a rarefaction. The spring is spread out a little bit behind the compression. Right? So different kinds of waves. Everybody with me there? Okay. Thanks, Tyler. You can let go of it and it'll come right to me. I'm really getting a preview of what it's going to be like to be really old, going up and down. So. Okay. So, with our longitudinal waves, okay, it's a series of compressions and rarefactions. To rarefy something means to make it less concentrated, thinner, okay, something along those lines. They often say that, like when you go to the top of a mountain, the air is rarefied. It's thinner than it is at lower altitude. So that's what a rarefaction means, to be less concentrated, thinner, okay, something along those lines. So when we see those, okay, we see the compressed region, we see the rarefied region or stretched region, okay, and in a longitudinal wave, unlike a transverse wave, the medium, that is the spring, oscillates parallel to the direction the wave travels. In the transverse wave, it oscillated perpendicular to the direction of travel of the wave. Okay, so that's really the only difference. Now, that's the difference in structure. Difference in behavior is additional to that. Okay? For a transverse wave, they generally slow down if they go from a medium that is less dense to more dense. Okay? They slow down. They don't travel nearly as easily in a more dense medium. Okay? It's why light slows down when it enters water and bends. Okay? It's why jewels like diamonds and things like that are cut a certain way. When light goes from air into the stone, it slows down considerably. And you cut the stone in a certain way to make the light reflect back out the top. What does that make the stone appear to do? Shine, sparkle. Okay? If the light gets out the bottom of the stone, it doesn't look nearly as nice. Okay? But when you look into the top of the stone, it looks like it's sparkling because of the way it's cut. Okay? It's actually how they can tell if a diamond is real or fake. Okay? So the difference between a diamond, okay, of either type, because there's what they call now artisan made, okay? They're made in a plasma chamber, so they can actually be grown artificially, okay? Versus a harvested diamond, a natural diamond, okay? They're chemically the same. So they behave the same way. But if you compare that to a cubic zirconia, which is made from zircon, which is a type of glass, okay? That's a fake diamond, okay? The way they're cut is different. A jeweler can tell that immediately. Okay? They put on the little monocle, okay? And they look at it through the monocle and it magnifies it, and they can tell a real diamond is cut with a certain angle, a cubic zirconia is cut with a different angle, okay, at the bottom, because they slow down light differently. Okay? They have a different, what we call an index of refraction, okay? And that determines the angle they have to be cut at to sparkle. Okay? So that's what an application kind of that. Now for longitudinal waves, they're the opposite. Longitudinal waves travel faster in more dense material. Okay? For example, the speed of sound in air is about 330 meters per second. The speed of sound in water is 1,500 meters per second. Okay? Longitudinal waves, because they're compressions and rarefactions, travel better in more dense material, because it's easier to compress and rarefy a dense material than it is to make the dense material go up and down. Okay, does that sort of make sense? So earthquakes produce both kinds of waves. Okay, if you get a really high magnitude earthquake, you're getting a lot of transverse waves. They don't travel very far, okay, because they can't travel through the Earth's crust very well. But longitudinal waves can go right through the Earth's crust, into the mantle, okay, and bounce off the other side of the world and come back. What do we call it when they come back? Aftershock. An aftershock. Okay, aftershocks are predictable. Okay, it's pretty reliable to predict when an aftershock will occur. Okay, based on the direction of where those waves are going to travel. Okay, so longitudinal waves travel better in dense materials. Transverse waves travel better in less dense material. All right. Okay, so longitudinal wave, okay, alternating disturbances of compression and rarefaction. Okay, if we mark one particular ring on the slinky, okay, so this would be the dotted line here would be the equilibrium position. Okay, the compression starts here. Okay, it's coming towards that marked piece. When it gets to the marked piece moves forward and then backward. But a little while later, the compression is way out here. Okay? The slinky isn't moving from A to B. The slinky is just oscillating back and forth. But the wave is traveling along the slinky. All right? Everybody with me on that? That's why we said yesterday, like, waves are not traveling from point A, or sorry, the medium is not traveling from point A to point B. If it was, there'd be a hole in the middle of the ocean because all the waves are crashing on the shore. Okay? If the ocean was actually moving with the waves, all the water would be over here, okay, and not be replaced by anything. All right, so make sure you have that definition there, okay, of a longitudinal wave, because that will be important. All right, so when we're talking about waves, okay, both types of waves, okay, they're produced by something oscillating with simple harmonic motion. Okay, so we've already talked about this. The length of one complete cycle, whether that is a transverse or a longitudinal wave, okay, is going to be the wavelength, right? The maximum distance from equilibrium that the medium is going to be disturbed by the wave is the amplitude of the wave, okay? And then obviously you've got period, frequency, all of those same things, excuse me, that we talked about before. Okay, so amplitude, okay, like we said, maximum excursion of a particle of the medium from the particle's undisturbed position, okay, and that is in either direction. If it's up, it's called a, what's the up part of the wave called? Crest. What's the down part? Trough. Okay, all right. We talked about that stuff yesterday, so we can skip over that. Okay, and wavelength, which is denoted by lambda. Guys, you don't have to, like, when you're denoting lambda on your sheet, don't spend a lot of time trying to make the curls, okay? Just, it's a short stick supporting a big stick. Okay, that's all you have to do with that, okay? So, wavelength, remember we said I demonstrated that yesterday, right? The distance between any two successive points on the wave, okay, is the wavelength. Okay, it doesn't matter what point on the wave, the next point on the wave, okay, equal to that one is exactly the same distance away, okay, as we go along the wave. All right. Okay, and then the time it takes for one wave to go by you, the period, the number of waves that go by every second is the frequency. Okay, all of that stuff we talked about yesterday. All right, so a good analogy of this is, okay, a train. Okay, so the length of a car is like the wavelength. Okay, the amount of time it takes the car to go by is like the period of the wave. The number of cars that go by in a second is the frequency of the waves. Okay, things like that. Now, when we talk about the universal wave equation, which is where we're going next, okay, it's talking about the relationship between the speed of a wave, the frequency of a wave, and the wavelength of the wave. Okay? Here's something that I'll say over and over and over again that's crucial that you remember it. The frequency of a wave can never change. Once a wave is produced, its frequency will never change. Okay? I want you to think about that because if you've ever like gone swimming where they had like the music coming underneath the water, I mean, obviously the music sounds different under the water just because our ears are not designed to hear underwater as well, but does the song sound the same? Like if you're above the water and then you go below the water, does the song sound the same? Same notes? It does. It's the same frequency, right? If I'm like, if we're listening to somebody, singing a really, really high note above the water and then we go under the water, we still hear that high note. Okay, it sounds a little bit garbled, okay, just because we're under the water, but the frequency of the sound, the pitch of the sound is the same, whether I'm above the water or below the water, okay? But have some properties of the wave changed when it goes from air to water? Which one property for sure changes when it goes from air to water? Speed. Yeah. The speed has to change. The medium is what controls the speed of a wave. So any change in the properties of the medium changes the speed of the wave. So that's why we were talking about yesterday. As a wave approaches the shore, it slows down because the depth of the water, which is a property of the medium, is changing. Okay? Now, if frequency is going to stay the same and can never change, then that means that if I isolate the frequency, and it can never change, if V changes, what does lambda have to do? Change as well, and in the same way, in order for F to stay the same. So no matter what happens to V, F has to do the same thing. So if waves travel from a medium where they're fast to a medium where they're slow, the waves have to get shorter. Okay? Because speed got lower, wavelength has to get lower. Okay? If the waves go from a medium where they're slow to they're fast, okay, then the wavelength has to get longer. But it naturally does that because of the nature of waves. Okay? The front part of a wave is always going to encounter the new medium before the back of the wave. So it gets a chance to run away from the back of the wave if it's speeding up. Or the back of the wave gets a chance to catch up if it's going into a slower medium. Okay? Which I'll demonstrate here in a minute. All right. Okay, so like we said, waves are going to be produced by an object that's oscillating, a source that's oscillating in simple harmonic motion. Okay, when a mass on a spring oscillates, it makes a sinusoidal wave pattern. Okay? A pendulum would do the same thing. If I had a pendulum swinging back and forth in front of me, and I had like a little pencil or something on the back of it, and I pulled paper past that pencil while it swung back and forth, it would draw a wave on the paper. Okay? Simple harmonic motion always produces a waveform. Okay? All right. Okay, so let's think about this. Just outside of town here, actually they just changed this again, thankfully, for whatever reason. Okay, but outside of town here, there's a spot where the speed limit goes from 100 to, well actually now it goes to 80. It used to go to 60, okay, which I never understood. Now it goes to 80 for about 25 meters, and then it goes to 60 after that. Actually, it goes to 80 for that first set of lights, I think now. Okay, so let's say we've got an area where the speed limit is changing. So on this side, we're able to go fast. Okay, let's say this is the 100-kilometer-an-hour part. Okay, and let's say that over here, the speed limit is 60, just so we get a big change. Okay, and I've got 3 cars traveling in this 100-kilometer-an-hour area. Okay, they've all got good following distance because, as we know, as we go faster, our following distance needs to increase. Okay, if I'm standing here, okay, and watching these cars go by, 3 cars will go by me every second. And so the frequency of cars going by me would be 3 hertz. Hey.
Have some candy grams.
All right, so out here, if I'm standing and observing, 3 cars go by in a second. Now, when this car crosses the line into the 60-kilometer-an-hour area, it's going to slow down. Okay, so it's going to go slower, but this car's not in the 60-kilometer-an-hour area yet. So what's going to happen to the distance between them? It's going to close up. And then this one will pass into the 60-kilometer-an-hour area and slow down. Okay, and then this back car will catch up to it. So a little while later, if another person is sitting here and observing how many cars go by per second, they're going to see this. Those same 3 cars are now traveling at 60 kilometers an hour, slower, but they're closer together. But the frequency of cars that go by this person is still 3 hertz. Okay? The frequency of a wave can't change because if speed changes, wavelength changes with it. Okay? Those are the 3 main properties of a wave that we're most concerned about. The speed of the waves, okay, the wavelength of the waves, and the frequency of the waves. And the frequency can never change. Okay? It's why the color of light doesn't change if it goes into water. Okay? If I'm looking, down into a pool and someone's dropped a red flashlight or something down in there, it still looks red down there. If I jump in the water and look down at it, it still looks red. Okay? The speed of the waves can change, but the frequency can't. Okay? And the frequency, it determines the color of the light. All right? Everybody okay with that? Okay. So does this analogy sort of make sense? So if we made this like waves, okay, that's kind of what it would look like, right? But now, okay, is the wavelength shorter? But so is the speed, but the frequency stays the same. Okay, everybody good with that idea? It's really important that we understand that the frequency of a wave will never change. I think I've said that 10 times now. Okay, super important. So we're going to talk about the universal wave equation, which kind of deals with this idea. Okay? So what affects the speed of a wave? The medium in which it travels. That is what affects the speed of a wave. Okay? That is what will change, increase or decrease the speed of a wave. The medium in which the wave travels. Okay? And we got to learn to use the universal wave equation in various situations, because for the rest of the unit, this formula is going to be your bread and butter. Okay? And it's pretty easy. V equals F times lambda. All right? So none of these questions are going to be mathematically challenging. Okay? What's going to make these questions challenging is the context of them. Okay? There's little tricks that I can play on you that test your understanding of how waves work. Because with that formula, I cannot test your mathematical ability. Okay? I know you can all effectively manipulate and use that equation. Okay? All right. So, how fast does a traveling wave move? Okay? Well, if we wanted to find that out, we could try and time it. Okay? So if I was watching a wave move along and maybe there's like 2 buoys, okay, or something like that, or 2 posts on a dock, I might be able to time how long it took the wave to travel from one post to the other, or from one buoy to the other, okay? And then I could measure how far it was between the buoys or between the posts, and then I'd be able to figure out how fast it was going, okay? What's the problem with trying to do that with waves? Could the wave change between the 2 objects? And is the shape of a wave fixed? Okay, as we're going to learn after Christmas, okay, maybe a little bit tomorrow, okay, lots of things can change the shape of a wave. So it's hard to determine, okay, the wave passed that post, oh, some other wave went over it on the way to the other post. I might not be able to track it very well, okay, because a wave is not a solid object, and so its shape can change. What might be easier is being able to determine the frequency of the waves and the wavelength of the waves, okay, that might be a little bit easier. So, we were looking at this yesterday, okay, how the properties of the water, in this case the property being depth, could affect how fast the wave traveled. So out here in deep water, okay, we've got deep water waves with swells, okay, and as we start getting close, that guy that they were interviewing was talking about how when the waves get to a point where the depth is half of the wavelength, they change from deep water waves to shallow water waves, okay, or surface going waves, he called them. Right? That's when they can get that wave shape, okay, like a breaker, peaking waves and breakers. Okay? That happens as the water gets shallower and shallower. Okay? But out here, look how far apart those wave crests are. Now look how far apart those wave crests are. Are they closer? They are. Okay? They're going to keep getting closer and closer together, and as they get closer and closer together, the wave is going to get shorter and shorter, which is going to make it go up. Okay, and get taller and taller. Okay, so what affects, okay, the speed of a wave is the medium in which it is traveling. Once you make it go into another medium, okay, it is going to change its speed. Okay, so we were talking about this at the beginning here, so I'll try and draw one of these. It's not very good. What's it supposed to be? It's supposed to be a diamond. Okay, good. Somebody recognized what it's supposed to be. All right, so what happens with a diamond is if you want the light that comes in the top, okay, when it hits the diamond, what it's going to do is it's going to slow down a lot. Okay, diamond really slows down light. Okay, and it's going to cause it to bend. And we want it to bend so that when it hits this facet is the side of the stone, okay, that it won't be able to get out. And it'll reflect off of this facet and go back to this facet and reflect off of it and come back out the top. Okay? In order to make that happen, the bottom of it has to be cut at a certain angle. Okay? That angle is dependent on the material. Okay? If it's glass, the angle is going to be different than it is for a diamond, okay? Or a ruby, or whatever gem it is that you are cutting. Okay? They all have a different critical angle, okay, at the bottom. Right, if I cut it at that angle, the light will come back out the top, okay, and it'll do this, okay, it'll bend again, and I'll see sparkling, okay, from that stone. Okay, so what the jeweler is looking for, if you bring in a stone and say, is this real or fake? All they have to do is look at that. Okay, a good jeweler would be able to tell you that almost immediately. The angle is considerably different. Okay, because for diamond, the refractive index is 2.42. For zircon, it's 1.92. It's a lot different. Okay, so light travels way faster in glass than it does in diamond. Okay, make sense? Okay. So all they have to do is look at that bottom angle. So lesson. Okay? If you're buying that ring for that special someone, don't cheap out. Okay? Don't cheap out. If they're worth marrying, they're worth the real thing. Okay? So get the real thing. And they'll find out. They always find out. I'm not speaking from experience. I was smart enough to get the real thing because my wife was totally worth it. Okay? But I do know of people who didn't. They find out, it doesn't work out. It doesn't turn out well. Not well at all. Okay? So get the real thing. It costs a little bit more. It's worth it. Okay? All right. So if we're dealing with waves, okay, the universal wave equation can be written in two ways. It can be written the way it is on your formula sheet. That's V equals frequency times wavelength, F times lambda. Okay? But it can also be written this way. V equals lambda over period. Is that the same thing? Because F equals 1 over t. Is this the same as saying lambda times 1 over t? It is. Okay, so it's the same formula. Just know that this version of it is not actually on your formula sheet. Okay, only F times lambda is. Okay. All right. So when we look at the units here, okay, just so we're sure we get the units, what are the units for speed supposed to be? Meters per second. All right, so units for speed are supposed to be meters over seconds. Okay, what are the units for frequency? Cycles per second, or per second. Okay, and what's the units for wavelength? Meters. So if I go meters times per second, that's what hertz are. Do I get meters per second? Okay, same thing I get here. If I use this formula where V equals lambda divided by t, I'm dividing meters by seconds per cycle. Okay, and we never say the per cycle part, we just say seconds. That's how long it takes. Okay, so we do get the right units regardless of which formula we use for that. Okay. All right, so a very simple universal wave equation question. Okay, it could be something like this. A sound wave has a frequency of 262 hertz and has a wavelength of 1.29 meters. What's the velocity or speed of the sound wave? So we take lambda, we multiply by frequency, and we get that the speed of that sound is 338 meters per second. Okay? Everybody all right with that? Pretty easy formula to use? Okay, here's where the questions can get tricky. What if I tell you that you're observing some waves and 10 crests go by in 4 seconds? And the crests are, so let's say 10 crests in, what did I say, 4 seconds? 4 seconds. And the crests are, let's say, 3 meters apart. What's the speed of the waves? Okay. Did I give you all the parts of that formula? The 3 meters would be the wavelength. It's the distance between 2 crests. That's the wavelength. Okay. I could have also said the distance between 2 troughs. Okay. I told you 10 crests go by in 4 seconds. What can you use that to get? Frequency. How many waves went by? Ten crests went by. How many waves went by? 9. Okay, that's what gets people. So, we're starting right here, right? So with our first crest. So 1 crest, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why didn't I say 3 crests? Okay, so I'm starting here, right? That's my first crest. The distance between those crests is 3 meters. All right, so if that's where I'm starting, that's 1 wave, 2 waves, 3 waves, 4 waves, 5, 6, 7, 8, 9. There are only 9 cycles, and that's a wave, a cycle, a full cycle in 10 crests. The same is true if there were 10 troughs. There's always 1 less cycle than the number of crests or troughs. Okay, so a question can do that. Sometimes a question will just say 4 complete cycles go by. Okay, well that's how many waves? It says 4 complete cycles go by. How many waves is it? 4. But if it says 4 crests go by, it's only 3 waves. Okay, just something we have to remember. It's about wave structure. If I start counting on this crest, and this is crest number 1, I am only going to get 9 cycles. Okay. Okay, so that's one of the ways a question could trick you. Okay, here's another one. Write this one down as an example. Okay, you shout at a cliff, because that's a reasonable thing to do. Okay, you shout at a cliff using a frequency of 500 hertz. Okay, you hear the echo from the cliff, which is 600 meters away. Okay, 4.2 seconds later. Okay, what is the wavelength of your waves? Okay, give you a minute to write that one down and try it. What's the trick with an echo? It goes there and back. How far does this wave travel? 1,200 meters. Echo questions are always like that. That's the thing that catches people on an echo question. Okay? In an echo question, the wave has to travel all the way there and all the way back again. Okay? So the distance traveled by this wave is 1,200 meters. The time it takes is 4.2 seconds. Okay? So what can I calculate with those two things? I can calculate speed, yeah, or velocity. Okay, in this case it's speed because I wasn't told direction, right? So V equals 1,200, okay, divided by 4.2. What's 1,200 divided by 4.2, guys? I forgot to turn on my calculator.
285.7.
285.7 meters per second. So it's probably pretty cold. That's a slow speed of sound in the air. Okay, but I was pulling numbers out of my head. So, all right. So we've got our speed there. What can I do with the speed since they told me the frequency? I also know that as a given. 500 hertz. How can I get the wavelength now?
Divide by frequency.
Yeah, we'll use the universal wave equation, right? V equals F times lambda. If I want to find lambda, divide both sides by frequency, and I'm finding lambda. Echo questions are a pretty typical type of wave equation question. So 285.7 meters per second divided by 500 hertz. Okay, it's going to leave me with meters. Okay, 0.571, no, sorry, we only have two significant digits, 0.57 meters. Okay, everybody all right with that? None of these questions, like I said, are going to be mathematically challenging. You're going to use V equals D over T, you're going to be using V equals F times lambda, that's it. Okay, but you got to be able to catch the little wave properties, tricks that are going to be in those types of questions. Okay, try this one. Person sitting on a dock, they notice that in 30 seconds, 6 crests pass by. The distance between the crests is 4.5 meters. Okay, what is the speed of the waves? Okay, give you a few minutes on that one. Okay, so 6 crests go by. How many waves go by? 5. Okay, so 5 waves in 30 seconds. So frequency is waves per second. So 5 waves in 30 seconds will give me my frequency. So 5 divided by 30, okay, there's my frequency, 0.16 repeating. Okay, hertz. All right. The distance between the crests is 4.5 meters. Okay, what did they tell me there? Wavelength, yeah. Distance from any two equal parts of a wave is the wavelength, so the wavelength is 4.5 meters. I know frequency and wavelength, V equals F times lambda, okay, and I take my 0.16 repeating and I multiply that by 4.5 meters, and I've got meters per second. Okay, so that number times 4.5, 0.75 meters per second would be the speed of the waves. Okay, everybody all right with that? I have on unit exams in the past given an echo question, okay, really no more difficult than the one I put up there, okay, and I've often given one of these as well. They're not usually worth a ton of marks, okay, because there's not much to them. Now, one other thing that can come up when we're doing wave equation problems is that they might tell you there's this sound wave traveling through air and the air temperature is this many degrees. If they do that, they're expecting you to use another formula that is on your formula sheet, and it looks like this. V equals 332 plus 0.6 times temperature. Okay, this calculates the speed of sound in air depending on the air's temperature. At 0 degrees Celsius, okay, sound travels at 332 meters per second at 1 atmosphere of pressure. Okay, we're never going to have anything other than 1 atmosphere of pressure. All right, and then whatever the temperature is, you multiply that by 0.6, add it to 332. It even works if you go into the freezing numbers because that number will be negative and it'll make the speed slower. Okay, and you'll get the proper speed of sound in air of any temperature. So if you're ever doing a question and they tell you, waves, these sound waves are traveling through 23 degrees Celsius air, you have to use that formula. Okay, you don't have to memorize it. As I said, it's on your formula sheet. Okay. All right. Try this one. It's an echo question with the air temperature. It's like I can see the future. Okay, so on this one here, the hiker yells at a cliff, and here's the echo 3.5 seconds later. On this day, the temperature is 22 degrees Celsius. How far away is the cliff? Okay, so what can I calculate with the 22 degrees? V, yeah. Okay, so V is going to be 332 plus 0.6 times 22. All right, so my speed of sound is 345.2 meters per second. Okay, and they hear the echo 3.5 seconds later. So how long did it take for it to get there? It took 3.5 seconds to go there and back. How long did it take to get there? 1.75, half of that. Okay, so there's one of two ways you can go about this. Calculate the distance for 3.5 seconds and divide that by 2, or just divide the time by 2 and get the actual distance, okay, in the end. So what I'm going to say is d equals v times t, and I'm going to use 345.2 times 1.75 seconds. Half the time is all it took for it to get to the cliff, okay, times 1.75. Right, the cliff is 604 meters away. Actually, we only have 2 significant digits, so 6.0 times 10 to the 2 meters away, which is exactly the same number I picked for the other question about that. Okay? All right, questions on those? So those are really the only tricks you can run into. Now, a couple of other things that might come up. What if the question says that the wave is a radio wave or an electromagnetic wave? What is it telling you about that wave?
It's longitudinal.
Actually, no, light waves are actually transverse. Okay, sound waves, like when we convert the light radio waves into sound, then we get longitudinal waves. But a radio wave and an electromagnetic wave are all forms of light. How fast does light travel? At the speed of light, yeah. Okay, which is one of the constants on the back of your sheet. Okay, so if you have any type of light wave, radio, electromagnetic, microwave, infrared wave, okay, any of those kinds of things, you are being told that the speed of those waves is 3.0 times 10 to the 8 meters per second. That is the speed of light. Okay? All right. Let's have you guys try those two first. Okay, let's have you try those 2 questions first. On number 3, okay, the dinghy is 250 meters from the shore, and it rises and falls 8 times per minute. Okay, what can I use that to get? Frequency. It rises and falls. That's a complete cycle. 8 times in a minute. Okay, so if I go and say that it's going to be 8 over 60, so I get it in hertz. Okay, I'll go 8 divided by 60, and my frequency is 0.133. Sorry, 0.13 repeating hertz. Okay, now he finds that it takes 3 minutes to get to the shore. All right, so if I know it's 250 meters to the shore, can I go 250 divided by 180 seconds? All right, that's 3 minutes. Okay, so that'll give me my speed of my waves. So 250 divided by 180. Waves are moving at 1.39 meters per second. Okay, now that I know frequency and speed, I can find the wavelength, V over F. Okay, 1.39 divided by 0.13 hertz. Okay, and that should give me my 10 meters. Okay, so if I take divided by that number there, okay, I get 10.4, but there's only 2 significant digits, so it rounds down to 10 meters. Okay, all right. What do we got? 128. Okay, we'll call it a day there. Okay, we're going to work on universal wave equation questions tomorrow. Okay, and then when we come back from the break, we will start wave behavior, interference, behavior at a boundary, standing waves, resonance, Doppler effect. Done. That quick. Okay.